Well, a very good evening, everybody. Jordan at Lasham this time, actually at Lasham. Hopefully that might fix the issues we had with the internet last time. Thank you for joining me. It's Meteorology Part 2. Hopefully you can all see the screen. I've got the chat on my screen as well. So hopefully we're not going to have any issues like last week, but I'm going to keep an eye on it. If we do happen to have an issue, I should better spot it a bit quicker. So yes, Meteorology Part 2. For those of you that might have missed Part 1, well, it's on YouTube now. Had to do a little bit of editing to it to make sure that it was concise and ready to go. But thank you for your patience with that. And this one will also be available a little bit later in the week. So as somebody was saying, Colin, you were saying a very suitable picture. Yes, well, we'll be having a chat about some snow a little bit later. But for now, let's have a look at the aims and introductions to this part. So last time we had a look at things like fronts, sort of global circulation, air masses, etc., etc. This time we're going to have a look at a bit more interesting stuff. First of all, starting with temperature, humidity, lapse rates and precipitation. We'll look at fog, mist and haze, other hazardous conditions, and a basic introduction to aviation forecasting. We will have a brief look at skew-T and sort of logarithmic charts to do with sort of soundings, but I must stress that it's impossible to do that within about an hour and a half or so, because I'm going to try and keep it to that no later. So got quite a lot to get through, but hopefully it should be just as enjoyable as the last one, and thank you again for joining me. So let's make a start. And we look at temperature, first of all. Temperature effectively, obviously, being the physical quantity for thermal energy for hot and cold. We generally look at temperature quite in detail in gliding to work out our cloud base. And we're going to look at how we might calculate a cloud base on rough figures a little bit later. Max day temperature will sort of show potentially when the highest cloud base is going to be obtained. And generally on a nice soaring day, this will peak sort of mid to late afternoon generally, and the dew point will reduce during the day. The dew point's quite easy to find as well. You could always use sort of what the temperature is just before sunrise as the most likely dew point temperature for the day. So yeah, dew point and temperature really important in what we're doing, and using sort of sites like GFS and Weather Online and such to find sort of what temperature it might be today is very useful. Bear in mind also that there are regional variations based on sort of land masses. So areas like London are going to have a higher temperature generally than areas like Lasham out here. Good example of that was when I did a cross-country flight from here to RAF Kenley near Croydon, where actually round here the soaring was rubbish, but the closer I got to London, the higher the temperature got and the better the soaring got too. And we'll look at sort of stable air masses versus unstable a little bit later. Compare temperature to humidity, and that's more based on, as we touched on last week, how much water vapor there is in the atmosphere. So yeah, two very important things: max day temperature and dew point temperature. But why is it important more than just numbers? Well, we talked about density altitude last week, and the fact that if the temperature is very high and the pressure is getting lower, then potentially the distance you would need to take off would increase significantly. Human performance as well, heat versus cold. If you're too hot, you're going to need lots and lots of water. You might get more tired easily, more likely to be sweating, and might need to drink a lot more water, so they need to go to the toilet more, etc., etc. Cold, on the other hand, obviously potential risk of hypothermia. That's more touched on in the human performance syllabus, but also thinking of materials and stuff like that, such as seat cushions, for example, which at low temperatures may not be so good at being energy absorbent. Then you've got sort of the weather in general, cloud base and visibility, where, as I mentioned earlier, the amount of temperature and the humidity percentage does make a big difference. Just look at my notes here to see if there's anything else. as I was sort of saying with humidity, generally when we get heavy rainfall, that's where all the water in the atmosphere is often rained out, and the water vapor content that we've got, the relative humidity, governs the amount of rainfall that will come out. The higher the humidity, the greater the water vapor and the more rain we're likely to see, and that's why tropical rain showers are often more intense than we have here in the UK. It also, humidity allows us to work out how it's going to feel for us. Obviously, if it's very, very muggy, if you've been to anywhere like Singapore, it always feels like your body's dripping. So yeah, that's why we don't go gliding in Singapore. But yeah, temperature and humidity are very important. Lapse rates. This is a little bit more theoretical when we talk about lapse rates. And although you can apply it in a practical sense, I do advise you to read a little bit more into the textbook with this one. So a lapse rate is the rate to which temperature in the atmosphere decreases as the altitude increases in most circumstances. A lapse rate tells us how much temperature is decreasing based on how high we're getting. But lapse rates do rely on various scenarios, and we're going to have a look at a few of those. First of all, the dry adiabatic lapse rate. Now, adiabatic lapse rates are affected by the atmosphere, either dry or saturated. They are also affected and cause the stability of the atmosphere to change. Dry or unsaturated air cools at about 3 degrees per 1,000 feet. This is known as the dry adiabatic lapse rate. This is a theoretical rate that can be calculated, and most air masses obviously will contain a reasonable amount of water vapor, but this lapse rate applies when the relative humidity is less than 100%. Now, adiabatic means that there's been no sort of change of state, particularly of the energy that is being effectively cooled as it rises. So yeah, adiabatic, when we're talking about that, is to do with energy changes. So that's the key thing there, is that we're looking at 3 degrees per 1,000 feet. That's the DALR. That is what is generally tested. What changes per 1,000 feet? And as I was saying, this does not apply if we have got to 100% relative humidity, because when we get to that stage, we get to the saturated adiabatic lapse rate. And that's when the parcel of air reaches the dew point and becomes saturated. Water vapor condenses, and condensing air will release energy in some form to evaporate it. That is called latent heat, which warms the air, and the lapse rate and the change reduces. Therefore, the saturated adiabatic lapse rate is more like 1.5 degrees per 1,000 feet. And as I was just saying, that's because cooler air cannot hold as much water as warmer air. This generally shows the start of the vertical development of the cloud, and is sort of around the same point as the dew point as well. So yeah, those two again, knowing that dry is 3 degrees per 1,000 feet, saturated is 1.5 degrees per 1,000 feet, and the difference between the two. So we've got to about 100% relative humidity. Once we got to this point, things are starting to condense. But there's one more lapse rate. That is the environmental lapse rates. If you took measurements of temperature at various sites, you could calculate this, which compared to the two, the dry and the saturated, is more unique because it's going to vary day to day. This measurement will show that the temperature does not always drop steadily with increasing heights, and this can be a little bit more realistic, and we can draw comparisons between the environmental lapse rates, the saturated adiabatic lapse rate, and the dry adiabatic lapse rate. And looking at, one too far, and looking at that, just looking at the two on their own, there's that 3 degrees per 1,000 feet through the atmosphere. We've got to the dry adiabatic lapse rate, and we've now got to the dew point, the condensation level, and we've now gone past 99% relative humidity, and we've gone to the saturated adiabatic lapse rate, which is now 1.5 degrees per 1,000 feet because the air is cooler because of that release of latent heat. But talking about stability, a stable atmosphere is where we can, and this is where we can compare things. We've got our environmental lapse rate here compared to the dry adiabatic lapse rate. If the environmental lapse rate is less than the dry adiabatic lapse rate, the air mass is stable. That is because the rising air will be cooler than the surrounding air and will sink. The atmosphere, therefore, is said to be stable. And if it is even more significantly different than the dry adiabatic lapse rate, the more stable the air mass becomes. Since the air, whether saturated or unsaturated, will always be cooler than the surrounding air. Because if the air particle is colder than the environment around it, then it is heavier and therefore cannot rise. Now, in these conditions, it's generally when we get subsidence, where you've got a high pressure and that air is cooling and descending on top, pushing down on the surface. This sort of condition will cause more sort of smoke, haze, and dust because this air gets trapped into something called a temperature inversion, which we'll look at as well. Because of the lack of sort of proper condensation in this and the lack of so much moisture, cloud formation is generally quite unlikely in stable air. Or if it does happen, it's not going to be particularly good for soaring. Compare that to an unstable atmosphere. And now air is unstable because when the air passes warmer and rises, it is lighter. It does so because it is lighter than its environment. The environmental lapse rate, as you can see in this one, is greater than the dry adiabatic lapse rate, and therefore we have unstable air. That is because rising air will be warmer than the surrounding air and therefore will keep rising because everything around it is slightly cooler and is pushing it upwards. In these sort of conditions, you're more likely to get cumulus, good soaring conditions, but there is a risk of if this gets out of control, it will potentially go to thunderstorms. And these sort of climates are probably more experienced in places like Singapore and on the equator as sort of a norm. I mean, you never ever get anything like sort of stability in Singapore at all, but out to where we are, we get a change depending on which air mass we've got for what air mass for what type of weather we get, whether it's sort of more stable, more unstable. And I mean, today it's been fairly stable, but in the UK. But as we start going towards the snow showers and stuff like that, and I think there was thunder snow a couple of weeks ago, we definitely know it's got a bit more unstable. I mentioned earlier about a very crude way of trying to calculate convective cloud base. And that is the difference between the surface temperature, or I should have written in there surface air temperature, because of course surface temperature is how hot the ground is compared to actually how hot the air surrounding the ground is. But it's surface air temperature minus the dew point times 400. So you've got an example there, 31 minus 16 times 400 is 6,000 feet. Now, this is again looking at humidity and comparing the two, because of course, if surface temperature, air surface temperature and dew point are the same, then you should expect to get 100% humidity. But interestingly, at times, especially during the winter, it might be 100% humidity, but potentially there are still no clouds. Always try and wonder why that is, but sometimes it's just not the point where the cloud starts to condense. Although as things heat up, and on a nice sort of winter's day here at Lasham, it's been quite common to see the fog is stuck in the valleys, it heats up, it comes onto the airfield, and it sort of ruins the day. We've only been able to fly to about 10:30. So yeah, don't trust this calculation completely. It's better when there's actual convection, as in thermals, cumulus, clouds, a normal summer's day going on. I've put in there about cloud base and ceiling as well. That's because there is a difference between the two, and it's not particularly well understood. Cloud base is the lowest altitude of the visible portion of a cloud. So with that, it could be any speck of cloud, as long as it's significant enough. If there's a cloud floating across the airfield, just one little cloud, the cloud base would be maybe 1,000 feet. But compare that to the ceiling, where if you've got that one cloud sat over the airfield at 1,000 feet, but higher up you've got a thick overcast layer at 4,000 feet, the ceiling is actually going to be that 4,000 feet, because that's covering more than half the sky. And it's important to remember this because if you think back to air law, and my colleague Michael Harrison did a fantastic presentation a couple of months ago, it's important to understand cloud base and ceiling, because we're obviously trying to fly VFR, and controlled airspace is becoming more prominent, and we need to make sure that we are keeping legal. So knowing the difference between cloud base and ceiling is really important. So yeah, something to take away there. Temperature inversions. Okay, so we've spoken about the stability of atmospheres, and temperature inversions will generally happen in a very stable atmosphere indeed. In some circumstances, you'll get to a point where temperature will increase with height. And that's because the lowest part of our atmosphere is, as we mentioned last week, the troposphere, which extends to about 16 kilometers. And this is where most of the weather happens, and is the section of the atmosphere where temperature would normally get lower the higher up you go. However, sometimes a small layer can form where the temperature increases with height. This is often called an inversion. This happens because in areas of high pressure, where the air high up often sinks towards the ground. As it falls, it dries out and warms up. This warm layer of air can act as a lid and trap cooler air radiating from near the surface. This is because warm air is more buoyant than cold air, so will tend to float above the cold air, a bit like oil and water. And that colder air gets trapped beneath the warmer air. This gives us an inversion, because if you were now to get in your glider or powered airplane and climb up, you would notice that maybe for the first 1,000 feet, it drops by 3 degrees or whatever. But as you get above that inversion, it starts to get a little bit warmer. Because this is inverted to what you would normally expect, it gets the name an inversion. Once the inversion has got below the dew point, cumulus will not form. So these are the typical conditions we call blue. And if the inversion is too low, potentially there will not be any soaring at all, because you will need temperature to push this inversion up. This generally happens in sort of high pressure conditions, as I said, and yeah, there's normal really hot sunny days where it's better to go for a barbecue than to go gliding. So yes, or maybe go power flying as well, because in these conditions it's not good gliding weather. Although people will generally think, gliding's based on heat. It's actually based on instability, not based on actually how hot it is. Looked fairly reasonable out there today for maybe a bit of gliding later in the afternoon once the stability went away. But good photo here of a fairly typical city. I'm not too sure which one this is, but I imagine places in China and stuff like that, where there's a lot of manufacturing. Soot, smoke, stuff like that will get trapped underneath it, while the clouds might poke out the top. Soundings. Okay, so we're going to have a look at what a sounding is and what goes on. So effectively, a sounding, an actual sounding, is when somebody sends a radiosonde, a weather balloon effectively, into the atmosphere high up. And it's done in certain places to make sure airliners don't come and hit it. This radiosonde effectively allows us to measure all the way up. It's got equipment in it to measure what's going on with the temperature and the dew point all the way up. And it comes back down, or it gets, probably in the modern world now, gets transmitted to a computer, and they can read and have a look at something like this, which is an ascent. Now, there's quite a lot of stuff on there, and potentially this balloon has gone up to sort of 30,000 feet or so. And as I say, we're not going to try to cover everything, but effectively, the basic here is temperature, as you can see, is it's quite small on my screen, But you can see temperature is increasing with height close to the surface because it's this is a inversion close to the ground. You can see then it cools as the line goes to the left, because you've got on the x-axis here temperature, and y-axis here you have pressure, effectively the same as altitude, because you can see as you get higher the air pressure reduces. So altitude and temperature, and you can see here that the line goes to the right as it gets higher to begin with, a low level inversion. It's getting warmer. It's got to about 3,000 feet. It's getting colder, and look, then it warms up again. The point where these two lines meet is effectively 100% relative humidity, where things start to condense. If they get close, it will also potentially generate cloud. Zooming in on that, just look at the directions of the lines again. You can see how that does increase briefly and then decreases again, and you can see how they get close. As we look at a blue day, you'll see that air reaches the inversion, which is this point here, before cooling to the dew point. You can see that, and the actual on this one, I think the air it reaches dew point much higher up on this one. But yeah, you can see the lines are spaced so far apart on this one that it's very unlikely that we're going to see much humidity and therefore much clouds. But you can see as the line goes to the left, the temperature is starting to reduce as we want it to. As the line goes then round the corner and starts increasing, that's where the inversion. So potentially on this one, this is probably again early in the day. We might only be seeing at 10 o'clock if we had a scale here. If you imagine here is about 1,000 feet, there's 2,000, 3,000, 4,000 feet, for example. Because this line's gone round the corner and then inversion's formed, we're probably only looking at convection up to about maybe 1,000 feet at best, which is positively useless. These sorts of days, because the lines are so far apart, there won't be any clouds, and you get gaggles, because we all don't like going to find thermals on our own. And yeah, so that's a blue day. Compare that to a cumulus day. And to bring up some more information here. You can see on this one, the lines are going in the right direction for a bit longer. Maybe the cloud base here, if we had maybe the 2,000 feet about here. The rising air is following the blue line, the dry adiabatic lapse rate at 3 degrees per 1,000 feet. It's got to the point where 100% relative humidity happens, and in this case, there is an inversion stopping the cloud from growing any further. You can see the lines are not particularly far apart from each other, which means there's an increased chance of clouds, probably just about enough cloud. If the lines are much closer, then potentially there's more clouds. If the lines become much farther, then we're potentially looking at it being more blue. Cloud top is generally, if you link these two together, you can see how that the line starts to go around the corner, and this little peak here, we start to look at how high the cloud has got to, because the dew point starts rising as well. So that is a cumulus day. Again, spend some time sort of having a look. I could do a whole presentation on this myself, though I'm not the expert on soundings. David Masson and many other very good meteorologists are better than me at this. But porous soaring conditions can be also found from the radiosonde, and that's because you can see how the lines are meeting here. Potentially we do have thermals up to 2,000 feet, but the lines have met here in the middle, and that means we've got a lot of cloud, because we've got 100% relative humidity at that point. So therefore we might see more stratocumulus spread out. You can also see that that line is a little bit stronger to the right as it ascends. So therefore, we're under a stronger inversion. The cloud can't really go anywhere, or the moisture can't go anywhere, so it will spread out and it will look horrible like that. There is still a chance that it will be soarable under this, however. Compare that to storms. Now, with storms, you can see that actually This sounding isn't showing a storm happening at the present time, but you can see here we are. Maybe it's a really, really hot day, 31 degrees on the ground by 11 o'clock. You can see that that's parcel of air is rising up and there's clouds forming quite easily because the lines are very close together. You can see this little bump here, which is another inversion. However, notice that it will not take particularly much for the temperature down here to increase, for that line to take a slightly different path, override the inversion, and suddenly we've got a temperature line going unopposed all the way to 40,000 feet, because that parcel of air is no longer being stopped by warmer air above it. So that parcel of air, therefore, will rise and rise and rise, and eventually will make a thunderstorm. And the lines are close all the way together, which shows that humidity is high. We're likely to get a thunderstorm. And bringing on to thunderstorms, there's Zeus, the Greek god of lightning, I think, or is it, yeah, I think it's lightning. My Greek followers in here will probably be able to confirm that, but I know I've got thunder. I think he is from memory. But necessary ingredients for thunderstorm are three big things: A, plenty of moisture; B, a air mass of warm, unstable air; and significant convection to lift that warm, moist air mass rapidly upwards. And that's what we try to make use of when we go soaring just before it goes to storms. And we did have a few storms here last year where people really enjoyed the soaring just before and were wondering why I was calling people back about half an hour before it started raining, because to them they were going, well, it's 8 knots up, the cloud base is 5,000 feet. But what they hadn't seen was the top of that cloud, as I was showing in the sounding, rising and rising and rising, and really was going to kick off very quickly. The three main stages in this life cycle are called the cumulus stage, the mature stage, and the dissipating stage. So let's look at those one by one. First of all, we have the developing and towering cumulus stage. So convection begins, and masses of moisture are lifted upwards by convection, by thermals into the air. This moisture cools and condenses, forming those cumulus clouds. The latent heat is released in this cloud, and because of that, we've got to a saturated adiabatic lapse rate. There's that line continues to rise, and that parcel of air continues to go up and pushes all the moisture up, continuing to condense all the way with clouds going up. And that grows into a towering cumulus. A towering cumulus, as you can see here, gets probably above the freezing line, and this is a key point because once we start getting above the freezing line, a thunderstorm becomes more likely. Remember as well, these are clouds, a towering cumulus, that we might take the risk of taking a cloud climb inside, and that's 0 degree line is really important, because although we're getting an 8 knot thermal all the way up inside this cloud, potentially as we get above the freezing level, we might start having problems with water ballast and icing and stuff, which we'll come on to shortly. But yes, the kettle is boiling in this situation. Then we get the mature stage, where the masses of moisture rises until a point where it reaches an inversion, because there are generally multiple inversions all the way up through the atmosphere. Potentially, that might be through the tropospores into the stratosphere. Once it reaches that, once that parcel of air can go no further, because it will stop eventually, otherwise there'll be untold amounts of horrendous energy, apocalyptical. It gets to that layer it finally cannot pass, and it spreads out, giving that famous anvil top. That moisture stuck inside that cloud has now become really large and heavy, and raindrops start to fall through the clouds. Cool air also starts to enter the clouds, and you start getting downdrafts, and then we start getting bigger updrafts, and the whole thing starts getting more and more, starts bringing more and more energy in and throwing it out. Those downdrafts sort of pull that those heavy drops downwards and start to make rain. But as we well know, it does not just produce rain, it starts to produce thunder, lightning, and hail. Not every storm that we get is guaranteed to have more severe elements. As I said, it's mostly based on the freezing level and how high the cloud is. Thunder and lightning generally occur when you get water droplets freezing and bumping into each other, causing that electrical charge. Finally, that electrical charge finds its opposite on the ground or within the cloud and will start discharging lightning. Most clouds are generally sparking inside, so they're not. Most of the lightning strikes happen in the world because there's millions each day or whatever. Most of them are going in between the clouds, whilst some of them will hit the ground, and occasionally some of them will hit other things, such as aircraft. We also get hail. I'm going to talk about hail a little bit later. And we're going to talk about gust fronts, and I might even be able to show you a little video on one too. Thunderstorms presents risks to aircraft large and small, and I think gone are the days where the great Derek Piggott, who obviously great predecessor at Lasham, was sort of soaring up in T21s up to 30,000 feet, and or wherever he was going to get gold heights and stuff. Those sorts of days are over. Generally, not just because thunderstorms, we understand, are very dangerous, but because the aircraft are more slippery and we're more likely to lose control of the speed within the cloud. But all good things, or all bad things, hopefully do come to an end, much like I hope COVID does. After a while, the thunderstorm starts to subside, and that's because eventually this thunderstorm's got so big it can't really get any more convection. It's stopped the energy coming in, and the downdraft starts to dominate. Therefore, the cloud can no longer have any fuel, a bit like a fire, and the droplets cannot condense, and therefore become rain or ice. The storm dies out generally to light rain and get those mammotus clouds, and it just sort of closes itself up from the bottom upwards. And you normally will look at that and go, "Ah, well, there's no more thunderstorm, but neither is it soarable because everything's damp and there's still some cloud in there." So there, those are the three types. But practically, there is a real risk to aviation. And I don't mind sharing stories from Lasham on this or other clubs that I worked at, because if there's anything that I want people to take away from this for this lecture this evening, is thunderstorms are not to be reckoned with, and things like that, like microbursts, are entirely possible no matter where you are in the world. I've worked for 2 different gliding clubs. Both have written off gliders in thunderstorms. Now, this wasn't even particularly a bad thunderstorm. It had passed nearby. Sometimes when there's a lot of air coming down out of the cloud, and there's a big load of rain with it too, that gets sort of pulled in together, and it comes down as one big large mass, and it hits the ground. When that air hits the ground, it doesn't just stop. It's got to go somewhere, and it goes left and right, and it flies out the side. Generally, you might see winds in excess of 30 to 40 miles an hour, sometimes even greater than that. Remember, something like a K13, as our poor M, or as it became W, found. 35 knots, 40 knots from a day which was maybe 5 or 10 knots. That gust is enough to turn over a glider, and even if you put tyres on them, they're still not infallible. So yes, do take gust fronts really, really seriously. In Australia, which I'm about to show you a video of a gust front which didn't damage anything, thankfully, there was a really nasty one which wrote off 3 people. Thankfully, nobody's been killed. Microbursts are also bad because if you try to land in one, because of the change in the wind direction here, it can become almost impossible to make a safe landing, because you might get suddenly a 20-knot headwind, 20-knot tailwind. US airfields in sort of the Tornado Alley in Kansas actually invest in millions of quid in technology, or dollars, in technology to actually detect these things coming. A gliding club is not going to be able to do that very easily. Obviously, there's a risk of getting struck by lightning. Gliders can take it. Obviously, there's the famous Dunstable accident many moons ago. It will write off the glider because gliders do not, especially composites, do not have a way of being properly taken apart and inspected. So generally the glider gets written off. I'm very happy to be corrected by an inspector on that, but I don't believe if you have a proper lightning strike that the glider is going to be able to be cleared by the manufacturer to fly again. Obviously, huge convective change, large sink and lift, so you could be having a great time and then land out 10k before the airfield because you've had 15 knots sink. Hail damage, icing, we'll come on to that in a moment. Rapid changes in wind direction. Tornadoes, they do happen in the UK, or funnel clouds. I've seen gliders try to get near funnel clouds. Probably best not to, because it can get quite scary. Same as a water spout, which might happen at sea. It may also change the readings on the SVID indicator. Now, what I'm going to do, I'm just going to change what I'm sharing, and I'm going to try to share a little video. Let's just stop a moment. Okay, let's get... yeah, soaring microburst. It's not so. I think that's a bit more frowned upon now. Right, here we go. Right, okay. Screen share. I have to change the way I'm screen sharing to do this. Okay, hopefully we can all see that now. Now, the frame rate's not particularly good on this because it's going to be streaming, but I'm just going to run this through and we'll see what we think of it. A storm is coming. Notice the clouds are starting to get a little bit taller in some places, getting a little bit bigger. I'm going to stop the video in a moment because I want to point out something. Right, okay. So hopefully, I'll just check we can all see this so far. We can see, this is Lake Keep It, where I used to work in Australia. Scandinavian pilot put this on the internet just after the Women's World Championships. We can see here we have a thunderstorm. Doesn't look particularly bad. I'll just bring that a little bit closer. Doesn't look too bad. We haven't seen any lightning strikes out of it. But you can sort of see how opaque this is. Maybe you can on the video. It's starting to show that maybe the rain's a little bit heavier. Now, let's look what happens. Oh, look at that. There's been a microburst. Now, would we have seen that coming? Well, it's not the darkest thunderstorm I've seen in the world. And as you can see here, quite a scary gust front. Well, Australians are a bit sort of desensitized to this. You look at that. Yeah, that's pretty serious. I'll just stop sharing again and go back to the presentation. Hopefully we made good of that. If anybody wants the link, they can ask me at the end about what they saw there. But I always think that that's really useful to see. Okay, right, let's go. Application. Let's get. Okay, so we've had our fun with the thunderstorms. Hopefully you understood that. Okay, precipitation. Precipitation generally forms when the air cools below its dew point and the water vapor within it condenses out as visible water droplets, mist, fog, cloud, etc., etc. If cooling continues and there's some turbulence or mixing in the air, then the water droplets come together to form slightly larger ones that are heavy enough to fall out of the cloud as rain, as we spoke about. If the temperature is below freezing, then snow or hail may fall. We can see on this diagram that quite often, especially in the UK, it's always snowing at heights if the clouds are above the freezing level, but it will come into the warmer air and it will fall as rain. Potentially, if there's an inversion somewhere and the warmer air is trapped higher up, the snow will come through, warm up, and will then go back into the colder air and will get super cooled, where it's reduced below zero, but it hasn't frozen yet. As soon as that hits the ground, you get freezing rain. Really dangerous on runways, cars, anything. Probably actually the most dangerous of the four types of precipitation here. So yeah, we definitely don't want to go flying. Sleet is where it's not quite it's not quite snow, not quite rain. The temperature is just on that borderline, and snow, as we're unfortunately about to see again this weekend, is where it just doesn't warm up at all. This can block aircraft instruments and degrade aircraft performance quite significantly, because all the droplets, all of the bits of snow on the wing will all stop the laminar flow, as we'll learn in Principles of Flight, over the wing, and will make the aircraft a bit more draggy. Droplets go into instruments and will block up tubes and stuff to the dynamic source for the airspeed indicator, and mean that the airspeed indicator gets stuck. Might not help any of the other instruments as well. Obviously, snow can form ice easily as well. When you fly through snow, it's a bit like going into hyperspace in Star Trek. Yes, I'm still old enough to remember that, even if it is the later series. Hail, on the other hand, is where water vapor sort of still condenses into tiny droplets inside a big cloud. Those go up inside into the top of the clouds. It can be very cold indeed, even during the summer months, based on how high the cloud's going. And as these droplets are swept in by the convection and they go into a very cold environment, they again become super cooled and they start to freeze as the temperature gets really, really cold up there into small ice balls. As that happens, there's not really much to warm it up as it comes flying through the cloud, because once it gets towards the mid to top bit of the clouds, you'll get into the hail growth zone, where the updraw air temperatures are generally maybe -10, -25. They, as I said, they bang together and often cause lightning. But once once a load of hail has sort of come together enough, as you can sort of see, it starts as an embryo, becomes a hailstone, and then gets larger. Eventually, it gets too heavy, comes out the bottom of the cloud, and because it's not really had time to warm up, it starts hitting the ground at some rate of knots. Obviously, the more that the stronger the updrafts, the more likely that a hailstone can get really, really big, and it just clumps and clumps together and come flying out of the cloud and start damaging cars and gliders. As I say, most prevalent in the severe thunderstorms. You really don't want to fly through hail because it really won't do your gel coat any good. But yeah, hail. Spectacular, but when you're at home. Check that we are still screen sharing. I think we are. Yeah, still good. Fantastic. Okay, next slide we go. Okay, icing. Okay. Icing generally will cause weight to be increased. It may also alter, if you've got a load of ice on the tail, it may put a big weight on there. And of course, again, it will increase the stall speed, as you can see on something like that wing there. It's not going to be very laminar. Again, the instruments may become blocked, radio communications may become a bit harder, and the runways become a bit more slippery, aka contaminated too. As I mentioned earlier, if we do take gliders into cloud, we need to make sure that we're doing so below the freezing level, so we don't end up with too much ice. That doesn't mean that freezing is impossible inside a cloud, but if we know where that level is, it's a lot less likely. In wave soaring especially, even though there's no exactly big thunderstorm around, if you've been up at 30,000 feet, the airframe temperature is very cold, the cloud's cold as well, has a load of moisture in it. You fly into a cloud, wings ice up, canopy ices up. We can't see anything, and you might have to end up having to warm the airframe up as you come down, which really is not ideal, especially if you're coming down at the end of a long day and the sun's already going down, because of course at flying heights the sun goes down a little bit later than at the ground, potentially behind a mountain. Oh, what happened there? Let's check that. I'm just paranoid about screen sharing. Right, there we go. Two types of icing: clear icing, rime icing, and mixed icing. Generally on the ground, we'll see if gliders come out of the hangar quite early in the morning, we'll see clear icing where that moisture in the air just touches the airframe and it just freezes. It's fairly smooth on top of the airframe, and as I say, super cooled water vapor in the air does that. Although it looks smooth, it's still enough to disrupt the airflow, and even if you remove it, the airframe may still be cold enough in the air with enough moisture in it that it will just refreeze. So quite often, a fiberglass glider is colder than a wooden aircraft because of the materials, and a glider might have to sit in the sun for a little while to warm up. Compare that to rime icing, where I've generally seen this more when I'm flying, because if I've flown through a snow shower, the ice sits on the front of the wing. That's because of it just follows the shape. Again, super cool droplets hitting the aircraft or snow. Mixed icing is a bit between the two. Quite cold, minus 15 to 20 degrees, especially if you're wave soaring, where it forms rapidly when ice particles become embedded in clear ice, and it's a bit more rough, and it may still do the wing. All in all, don't get ice. It's just not very good. If you've got anti-ice in a glider, let me know, because I don't believe any manufacturers do. And I don't think bug wipers would remove it either. But yeah, those are the three types of ice. Now, something which is not talked about so much on here, and I am going to take a slight divergence from the BGA syllabus here, is to briefly talk about carburetor icing, because this affects powered aircraft, but it can affect tugs. It does affect motor gliders, and there's more of you now doing motor glider training, either part of your gliding course or even maybe doing a motor glider rating yourself, which is, we're going to, at least at Lasham, we're rolling out a lot more. Effectively, naturally ventilated engines, most commonly found in sort of training aircrafts, your Venture, Slingsby Falk, your Cessna 152, are highly susceptible to carburetor icing. There are two main causes of this. The first one is because of the gas laws, which directly states that temperature is directly proportional to pressure. When the air intake in most of these aircraft uses a Venturi, the pressure sorry, I'll just read. The pressure will get a little bit faster, and that will change the temperature. And eventually the pressure may reduce as well. Sorry, I'll just read that again. The air pressure intake uses a Venturi, which drops the pressure inside the carburetor. As the pressure drops, so does the temperature, and the moisture starts freezing, restricting the flow to an engine. And that is what will eventually start to freeze that little bit of intake in the engine. These ice accumulations will stop sort of airflow getting through, and eventually it will start to choke basically the engine from actually operating, and it will eventually start to suffer, may even fail completely. This generally will happen between cruise power and idle, because the engine is not running and generating loads and loads of heat. Those we'll come on to in a moment. It's not purely down to those two. You always want to have sort of cold air in the engine, because the engine will run better on it, and hence we're always balancing the two rather than trying to have a heater running on that the whole time. But fuel vaporization can get in the way as well, because the Venturi effect is still happening. There's a cooling effect as fuel mixes with air, which causes the vaporization. That moisture condenses out of the resulting air, causing the ice to freeze. And that's more bad news for the engine. And again, we get that ice buildup, and potentially there might even be issues with what temperature the fuel is as well. But fuel temperature is not purely based on the on it being cold. it can also get a bit hot. Because if you're flying aircraft like Rotaxes, the fuel may sort of unleaded in not particularly well-built fuel tanks. The fuel may become so hot it vaporizes in the fuel lines, not allowing fuel to actually reach the cylinders. So the fuel basically just disappears as it goes through the system. This is why it's important if you're flying a Rotax aircraft in really, really hot conditions to check what the limitations are, because if you're operating much above 30 degrees, you are at risk of vapor lock. And if you leave the fuel tank and the aircraft parked in the absolute blistering sun all day and you get into it at 4 o'clock, you're again increasing the risk of a vapor lock. Ice can just in general also just cause problems by just blocking air intakes and things like that. It may block up other instruments and stuff, as we spoke about. So we want to avoid carburetor icing. We need to know when the risk is higher, and on this chart here we can see air temperature versus dew point. You can see a temperature of about 10 degrees and a dew point of 10, 100% relative humidity is the point where this is most likely to happen. But notice, anywhere where there's a high humidity content, there is a risk of there being carburetor icing. So it's not based on flying on the coldest day. Some cold days the humidity is quite low. Maybe you've got a temperature of 0 and a dew point of maybe -10. You're still not necessarily going to hit it so badly. It is really dependent on what is going on, humidity. So yeah, around these areas here. How do we get rid of it? Well, you can use the cowl flap in something like a Rotax Fog to control the heating of the engine. It doesn't really have a carburetor heat, but we can control the heats by that. Or the carb heat, which introduces warmer air into the engine, which does have the impact of actually reducing some of the power output, but it just burns away the ice. And if you see that drop significantly and then slowly build back up, you know you've burnt away the carburetor. You burnt away the carburetor ice. Watch the RPM closely to do that. Remember to ensure the carb heat is also being used at the right time. You don't want to find it's fully out when you want to do a go around, because otherwise you'll find the engine is not generating full power. And you can see on here a diagram of a cowl flap as well. And the fact if you close that up, everything keeps a little bit more warm in there. Aircraft that have got fuel injection systems don't actually suffer from this so much, but air intakes still can get clogged by ice, as I was saying, with impact ice. So you might need to draw air in from another source. But yes, the key thing to take away from this is it is based on the relative humidity. And the fact at low power settings, it will be worst, but you could still get carburetor icing at quite high ones. Okay, that's the end of us talking about ice. Thanks, Don. Pressure reduces in the Venturi. The pressure reduction brings the air closer to dew point and ice forms. I appreciate that. Me getting my words the wrong way around in that. Fog, right. Generally caused by high density of water droplets suspended in the air close to the ground. When that air is cooled close to the surface of the earth, the water vapor condenses more readily into a cloud, very, very close to the ground. It's generally defined in aviation in anything less than 1,000 meters. So fog for motoring is generally anything less than 100 meters. And I remind you that really fog lights shouldn't be used below 50 meters. Shouldn't be used above 50 meters because they just dazzle drivers. But we're not talking about cars. But yeah, 1,000 meters or less is fog. Makes airfield operations and landings tricky. Runway visual ranges, as I said there, we're going to see that happening as we get the snow coming in, reducing the visibility. Runway visual range is effectively where you've got a machine that fires a laser beam into the distance to another machine, and it works out how far there is, how much visibility there is, and sometimes it's down to 100 meters, which challenges even commercial aircraft. Fog can get mixed in with sort of smog, and it's generally trapped under an inversion too, especially in radiation type fog. And as I say, I certainly wasn't around to remember it, but there was those great smogs of the 1950s and stuff in the Clean Air Act, which sort of got that out, because at times fog you couldn't see past your hand. Fog can take many forms. Sort of, you've got here the regular type of fog where you can see an Airbus at Lasham's hidden by that. But you also get shallow fog, which is quite pretty. You might be tempted to go flying, but actually you might not be able to see the runway. It's a bit like being above the clouds, even if it's at 2 meters. Definition of freezing fog is just any fog at or below 0 degrees. Tiny water droplets just remain, again, become super cooled. We've heard that word a lot now, and freeze onto objects. And as I say, shallow fog can just be a meter above the ground, but make for seeing the runway really difficult to see. Let's have a look at some types of fog. We've got radiation fog. I've borrowed this image from my book, which was Very British Weather by the UK Met Office. You can see that when the night skies are clear, the Earth's heat radiates away into space. As the ground cools by convection, so does the air just above it. If a light wind gently just stirs the air just a little bit or isn't around at all, it may just reach the dew point and radiation fog will form. Because this air is cool, there is again that issue where the air cannot hold so much moisture, and therefore we get cloud forming very, very close to the ground. This is probably one of the easiest ones to burn off, because it's just purely heating needs to get rid of this sort of fog. Whilst other types, I mean, valley fog, as you can see here, the cold dense air is settled at the bottom of the valley. It's cooled, and again we've got we've got fog at lower levels, while higher up the hill potentially we've got less of the risk of fog, though this fog can lift in the morning and become low cloud and plague areas higher up. We see that at Lasham. We're 600 feet above sea level here, one of the highest points in Hampshire, and down towards Basingstoke or Odium, it's 400 foot lower, and potentially there's fog there. We don't have it. That did actually happen today, because I could see Farnborough was struggling to get jets in whilst it was perfectly all right up here. And an inversion normally stops that cloud from jumping up. Advection fog normally happens when moist warm air passes over a colder surface and is cooled. And as you can see, as that happens, the air again condenses and becomes a cloud. We see this a lot in fronts, and we can see that if we get sort of a warm front coming through, and it sort of just comes off the seal, comes well inland, and we just get that fog. Orographic clouds is when wind is blown up the slope and the air will start to cool. Again, will condense and the cloud will form there. Hill fog is the same. It might be that it starts at the bottom and slowly makes its way up. Orographic cloud can really happen even with very slight slopes. We see it at Lasham, where down in Alton or at Odium, we've got it's nice and sunny, but the air's come up the hill and it's condensed and makes a cloud. Really annoying. And finally, just one more, it's not so relevant, but evaporation fog caused by cold air passing over warmer water. And again, that warm water eventually evaporates into the lower layers, mixes with the cold air, again, can't hold it and condenses. And we see this sort of saunas, swimming pools, stuff like that. But that won't really affect gliding clubs as much. Compare that to mist and haze. People will sort of think it's fairly similar. But and to some extent it is, because with mist, at least, it's similar because the water droplets are still condensed. It's still suspended in the air, but it's just at much less density, so we can just see through it. It's not so opaque. And relative humidity is still high, between 60 to 100%. And the key thing is here, visibility is between about 1,000 and 5,000 meters. Compare that to haze, where actually we've not got water droplets. Instead, we've got fine particles of dust. Maybe we've got a tropical continental or something like that, and it's coming up from the south. We get these Saharan plumes, where it's sort of these bits of Saharan dust get carried all the way up here, and eventually it gets to the UK, and it lands on cars and stuff like that, and it becomes really, really hazy. As I say, it's not linked to humidity as much, because for it to be classified as haze, the relative humidity must be less than 60%. Again, though, it will generally be between 1,000 and 5,000 meters. So fog below 1,000 to 5,000 meters, depending what it is, either mist or fog. Smoke can get in there too, but gone are the days of burning lots and lots of stubble. Okay, getting through. Charts, the Met Office are really, really good. Well, they have to be. Produce charts such as this, the Met Form 215, which provides a forecast of in-flight weather conditions below 10,000 feet for about a 9-hour period, and it's updated about 6 to 8 hours before. It's designated for either an area or route forecast. So let's say if you're going cross country, you can see what conditions there are further up, and you can see it's basically a very detailed synoptic. I won't read through everything here, but you can sort of see there's lots of information from what the synoptic is telling you, and it's divided into areas, as I said, A, B, C, D, E, and areas like A1 will have a sub-note in here somewhere. I think it's that black bit there. And there's lots of information. This bit here is taken out of Skyway code. All of this data is provided free of charge via this link here. If you go there, you can have a look at how to sign up. Very, very useful indeed. And there's lots of guides on there to help you. But the Met Form 215 is something very useful in gliding to work out a sort of general synopsis at a great detail. So if we were at Lasham today, I'll be looking at that going, well, we're in a warm sector. We're probably going to see a fairly low cloud, maybe some poor visibility and some changeable conditions. But the freezing level, as demonstrated here, this was taken in February. Freezing levels are not too low in this example. They do have the 214 as well. The 214 will show wind and upper winds and temperatures for the UK. Both of these charts, by the way, have European counterparts. Just because of Brexit doesn't mean we've stopped doing that. Met Office don't care about that too much. But these will provide upper winds and temperatures. And although, as you can see, it can't provide something for everywhere, you'll see if we were trying to work out Lasham, which is here, we would use maybe an average of 2 or 3 boxes. So from here, I can have a look. Maybe I'll just look at this one. At 2,000 feet, I'm expecting 15, or maybe 17 to 18 knots at 200 degrees. You got the height of the altitude here, so 1,000, 2,000, 5,000. Direction in degrees. We have the wind speed and we have temperature, and you can see the freezing level somewhere between 5 and 10,000 feet. So again, very, very useful charts. They also produce warnings, and this is actually a valid warning at the moment for the UK, for Lasham for the rest of the day and into tomorrow, looking at slight to moderate snowfall. These are separate from the public sort of weather warnings. The weather warnings in aviation happen a bit more frequently, simply because we're obviously doing slightly more hazardous things. So yeah, you'll see stuff like where frost is likely and when snow is likely and when even winds that are not actually that strong are around. We're sort of looking at something this weekend called the Beast from the East 2, as the media likes to call it. Effectively, what a beast from the east is when cold wintry conditions in the UK come from the east off the near continent. This normally happens when there's a high over Scandinavia or a low just south of us, as is the case at the moment, dragging colder air off. And you've still got Atlantic weather systems coming up against very cold air. As those two meet, and depending where the boundary is, those on the warmer side will get a crappy rain day, those on the colder side will get snow, and that boundary is basically slap bang over the middle of the country at the moment. I think down towards the West Country you're not going to see so much, but out towards, I know, East Anglia, sort of Essex and Kent, it looks pretty bad, and I know there's an amber warning, a public warning there for that. But yeah, Beast from the East is coming. And I know we've got, I think, feel like temperature here looks like -10, so really, really not very nice. And as I was saying, temperature does affect our ability to fly. METARs and TAFs, these are aviation forecasts and terminal aerodrome forecasts. As I say, reports and forecasts. Larger aerodromes will produce longer forecasts. Heathrow and stuff have more detail and will be very useful to people all around the local area. So for here, I would look at Heathrow or Bryce Norton, for example, to have an idea of what's going on, because Farnborough doesn't do a forecast to the morning, and we might be able to see a change coming a little bit earlier. It may be best to look at these on a map rather than actually just one by one, because you'll get a better picture of what's going on. They're generally updated every 30 minutes, TAFs every few hours. The military have this code system, as you can see here, where they got a bit lazy and they don't want to. I won't say lazy. They've shortened their way of doing things into color codes, so blue, white, green, or whatever. So generally for gliding, we're looking at something either white or blue to do something like this. We're going to have a look at a bit more detail in this. You are expected to be able to decode these, and we'll go through a pretend one in just a moment. But yeah, METAR's reports, TAFs are forecasts. Here we go with a METAR. So I've just broken that down for you. So this is obviously an actual report, a meteorological report at the time. We're looking at the 28th day of the month at 13:20 Zulu. Weather reports are always done based off Greenwich Mean Time. Even down in Australia, they're still using that. The wind here, as you can see, is coded as 070 degrees at 05 knots. So east northeast at 5 knots. And you can see the wind is varying in this example, varying between north and actually a bit of south in there as well, 130 degrees. All the nines, as you can see here, means visibility is greater than 10 kilometers. That's the greatest visibility we can get in the UK. I say that this is the greatest visibility we report in the UK. We don't report 20k. If you want, if there is slightly less visibility, it might be 5,000 meters or so. Cloud base is then next, or so the first bit of cloud, as you can see here, is a few 4,500 feet, temperature 21, dew point 7, and the QNH, the sea level pressure at Southampton, of 1032 hectopascals. You can see here that we'll either use few scattered, broken, or overcast. Sky obscured is also used at times if it's really, really hard to tell. Remember that cloud base is always based off QFE. So height above the airfield, that's how high the cloud is, because that's where the ceilometer has found the cloud. So be careful if you are sat on top of a massive hill and you're, let's say if we are at the Mind and we're getting Birmingham's METAR, well, there's a big difference between the Mind and Birmingham, not least that they're almost not in the same country. So of course, the Mind definitely is in England, as it is commonly forgotten. If there is uncertainty to the forecast, and we'll look at that or uncertainty, then probabilities might come in. But let's have a look at that, because as we look at a TAF, a terminal aerodrome forecast, we're going to look at something very similar. Here we got, again, this is when it's issued. This is not when this is not a report. This is a forecast. This is when the forecast was issued, 20th day of the month at 0724 Zulu. This says between on the 20th day, 7 o'clock to 15, we are looking at 350 degrees at 10 knots, greater than 10 kilometers, broken at 1,200 feet. So that's the general weather between those two times. Now we get a little bit more in detail here, because there's maybe a bit of a couple of changes that are going on during the day. Tempo, it's showing here temporary between 7 and 10, 6,000 meters, showers of rain, broken 800 feet. Okay, so we know that there's a reasonable chance. A tempo means it's almost certain that something at some point this will happen. Whilst it says then becoming later in the day, from 10 o'clock to 13, scattered 3,500 feet. So yeah, the becoming bit is the bit you want to look for, because as you can see, this has set a general tone of what's happening. but as you get towards the end of the period, it's showing that things are improving. If there's significant significant doubts in the ability of this to happen, then that you may get Prop 30 or Prop 40. So Prop 30 is generally said in aviation it probably won't happen, and Prop 40 means it probably will happen. There's no Prop 60, there's no Prop 80. I don't know why that they've chosen those two, but weirdly, 30 is almost not going to happen, 40 is likely to happen, and tempo is definitely going to happen. So yes, rule of thumbs there. METAR codes, I won't keep that on the screen too long. And thank you, Martin, for looking at the decoding of these ones. There are quite a few. If you just type METAR TAF or things like aero weather and stuff, I won't plug anything because not all the apps have had a particularly good run over the winter. Some of them have had data connection issues. But yeah, certainly you can decode a lot of what's going on via these sorts of apps. But to give you an idea, you can see some of them are quite easy to see, like drizzle, for example, which is just very, very fine rain, not big droplets, is DZ, SN, snow. But then you get things which are very difficult, like BR is mist, GR is hail. I don't know who actually designed the METAR way of doing things. It does sort of work, but only when you get to know them. And you have minuses when it's light, plus for heavy. If it's moderate, there's no plus or minus symbol. It's just the type of weather. And VC means in the vicinity. So yeah, qualifier is sort of says, is it good or how bad, what's happening, and then the sort of on the descriptor, and then you've got precipitations and whatnot. So yeah, lots and lots of codes to learn. But again, as Martin was just saying, there are ways to learn that. And thank you, David. BR from the French. No, we've got two things. Broom. Yes, I agree. It's or FU for fume for smoke. Getting there now, folks. Sigmets and ATIS. Sigmets are where within the airspace, well, within the whole sort of sovereign airspace, the Met Office or Air Traffic Control will put out a significant meteorological information, which is when effectively if an airline has gone, wow, it's really, really bad, the turbulence is bad up here, there's been there's a fairly nasty lee wave rotor system up there, then they might report that, or they might already know it's coming, so they put that in a SIGMET, which can be sent to the pilots. We can access SIGMETs from the Met Office sites, and also a site called SkyVector. But for gliding, they're not particularly relevant, if I'm honest, because when SIGMETs are about, normally the weather is pretty poor. You do get ashtams for volcanoes. A volcano that I won't even attempt to pronounce in Iceland put out a load of those. And you get snowtams, which will be quite important over the next few days for information relevant to snow at an airfield, such as how deep it is, how long it might take to clear, braking action reports, etc. ATIS, I think Automated Terminal Information Service or something like that, is effectively a recording played at big airports such as Farnborough, Heathrow, and it plays basically METAR and airport information, update every 30 minutes. Generally updated 10 minutes to the hour, 20 minutes past the hour, though sometimes if there's a significant update, they will move it forwards. You also have volmets, which I did mention in my communications presentation some time ago, on effectively continuous radio broadcasts of lots of different airports' reports. And this can be useful if you're doing a long distance cross-country flight in a powered aircraft and you don't know what the weather's like at the other end. Though the friendly folks at London Information can also relay weather reports by air traffic. And there's a few frequencies there. Sometimes there is a question on volmet in the exam. Of course, the perfect gliding day, as we come to the end here. Generally, we would want the air to be fairly close to the centre of a high or the axis of a ridge. So most times a ridge of high pressure comes over the UK. We want long daylight hours. we want pressure between 1017 and 1028. That's generally just about right. We don't get too much instability. Isobars with a strong anticyclonic curvature, again, not bringing in fronts or any excess moisture. We do want a somewhat northerly component to the wind in the UK, at least in the south, because generally it's a slightly drier air mass if it's coming from the north, but it's also just unstable enough and not to cause thermals, but not so unstable like a southwesterly where we might end up getting more showers. A weak cold front, which doesn't bring too much rain, is quite nice as well because that just destabilizes the air enough. And wind's not particularly strong. And of course, the bigger spread between temperature and dew point, the higher that cloud base, as we remember earlier. Thanks, Don, for granite rain, hail. Useful weather links for gliding and power flying. I don't support one particular brand here at all. As you can see, they're all about the same size. So RASP, if you want something for free. Top Meteo, it's okay. Top Meteo resolution could be slightly better. Met Office is obviously a good source of information. Sat24 for satellite images. SkySight has taken off really well recently. Again, a subscription. Similar to Top Meteo. Weather Online, which does all the GFS, I say GFS Global Forecasting System, the American models, that brings up temperature and dew point spreads. My favorite probably is Windy, because Windy, which is a free app and website online, can just show you so much graphical representation of what the weather's doing. But I mean, SkySight closely follows behind that in its ability to do that. My favourite, though, of all forecasts are cross sections. I wish I could draw them. I would like to, and thanks Evo for talk about Windy takes information from Meteo Blue. You can change the models on Windy, though. You can choose the European model, you can choose the American model to do that. But cross sections, I say, my favourite forecast that Glider Pilot can receive, because it just shows it perfectly. If I'm coming into flight competition, I've got all the information I need there. I almost thought that was a funnel cloud on that day, but you've got all the thermal strengths, you've got all of the heights, you've got the freezing level. It's just perfect. If any of you are competition organisers out there, please try to keep cross sections going, because I do find that some competitions are not doing them anymore, or you get Met men in that don't want to do them. I just think they are the best way to do it, and actually I wouldn't necessarily need to have a massive Met brief at a competition if I can see the cross section, because most of the information is on there and it can be reviewed just before takeoff. So yeah, the RAF do them all the time, and I'm envious of those GSA clubs that get a cross section each day before going flying. We have to put up with generally satellite pictures, which Sat24 does very nicely, and we can pick up all of that information from there, and we can see quite a lot, as we can see here on a summer's day. We can see the weather clearing off to the right and stuff burning back. The infrared generally will show the higher level clouds compared to the lower level cloud shown on the visible. We might also be able to pick up sort of lee waves if we see sort of lumps in the cloud system on the satellite. And a picture like that is generally when we're going to go and set some records. Perfect day, middle of June. I remember it, June the 1st, 2018. Absolutely perfect. 1,000 kilometers done by many pilots that day. And hopefully we're setting ourselves up for a fantastic spring, because I can tell you, January and February, even if we could have flown, were pretty awful. As we reach the end there, I've got a couple of questions to give you. We're going to finish up on time. What's the cause of hill fog? What's the appropriate approximate rate of change of temperature with height of the dry adiabatic lapse rate? And what are the three main stages in the life cycle of a thunderstorm? I'll give you a minute to do that, and we'll come back very shortly. Another 30 seconds, and we'll just finish off. Okay, so what do we think? Don't put the answers in the chat. Let's just go through this. Well, we have A for all of them on this one. Moist air forced uphill and its temperature reduced below the dew point, the cause of hill fog. Approximate range of temperature with height for the dry adiabatic lapse rates. That's 3 degrees loss per 1,000 feet height gain. And the 3 main stages in the life cycle of a thunderstorm: the cumulus stage, the mature stage, and the dissipating stage. Okay, fantastic. And that brings us to the end of meteorology. I appreciate that it's been quite a long one. We've probably done about nearly 3 hours worth of theory in total. Yeah, I really hope that you've enjoyed this series. It's probably been a little bit different. My ethos is to try to do this just keeping it simple. I could chuck you loads and loads of data, but for a glider pilot or private pilot, you just need to know the core things that are going to really affect your flying. So plenty of reading to do, but yeah, I think I think given that and a bit of reading, you would be ready to sit the bronze exams. As I said to CFIs before, please make sure you are allowing your members to do the exams online, because it is easy to do on there. And if you need any help, I'm even more than happy to come and give you a tutorial on how to do that. So